Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 67, and it is entitled Capacitors and Capacitor Energy. Capacitors! A new electrical device for us appears in this lesson. At first blush, the capacitor may seem like a lowly, humble device. After all, it seems fairly boring, consisting of a pair of conductors separated by an insulator. In its simplest form, a couple of sheets of aluminum foil with a piece of wax paper in between could serve as a capacitor, a sandwich made out of basic kitchen materials. Getting even simpler than that, take away the wax paper and somehow keep the sheets of foil from touching each other so that only air remains in between the gap, and voila! You've got a capacitor. But put this device in an electric circuit, especially one that contains alternating current signals, and the capacitor becomes a dynamic player in electronics, helping tune resonating circuits in radio transmissions, smoothing out wildly varying voltages in filter circuits, storing energy and releasing it in the twinkle of an eye. When you flash a camera, you're using a capacitor. In the AP Physics B course, the interesting applications of capacitors don't appear in the curriculum because they require calculus to solve the problems. But because capacitors are ubiquitous in developed societies, it would be a disservice to bypass them completely. They will likely appear in at least one problem or question on the AP exam, so you need to know how to handle them. Your authors lay out capacitor basics in a straightforward way. The parallel plate capacitor is the most common type you'll encounter, with plate area A and plate separation D. Often you'll see this sketched in a side view. Many times air serves as the insulator between the plates, and the formula for the capacitance of the device is given by C equals epsilon naught A over D. Epsilon naught is called the permittivity of the vacuum, and it's a number that's going to be the same number in every problem, and it measures how easy it is for an electric field to penetrate through whatever insulating material is in between the gaps. Numerically, epsilon naught is equal to 8.85 times 10 to the minus 12 coulombs squared per Newton meters squared. This number is not one of my good friends, so I wouldn't bother trying to remember it. Farads are the units of capacitance. Named after Michael Faraday, the great British experimentalist of the mid-1800s, a farad is a huge amount of capacitance. So more often you'll see the units picofarads, nanofarads, microfarads. So make sure that you work in the proper exponents when you're solving problems. I hope we'll have an opportunity in class to dissect a capacitor and see how it's put together. Well, what happens when you put a capacitor into a circuit? Let's take a look at a simulation, and this link would take you to that simulation. In this simulation, you can adjust the different parts of the capacitor. When the battery is connected in the circuit, then the capacitor can become charged, making opposite signs of charge appear on the plates. The battery pumps negative charge from one plate to another, like this. I'm moving the voltage, and you can see that charge appears on the plates. A uniform electric field appears between the plates of a parallel plate capacitor. We say the capacitor is charged when separation of charge has taken place, with just as much of one sign of charge appearing on one plate of the capacitor as the opposite sign of charge appears on the other. So how much charge appears on the capacitor? The equation is given by Q is equal to C times V. Q is the amount of charge that appears on each plate, and that's in coulombs. V is the difference in potential, or the voltage, between the plates, in volts, usually caused by a battery. And C is the capacitance of the capacitor in farads. Typically, the amount of charge is going to be measured in picocoulombs, nanocoulombs, and microcoulombs, so make sure that you use the right exponents when you're solving problems. Let's work an example problem. A 2.5 microfarad capacitor contains a charge of 5.0 times 10 to the minus 5 coulombs. What's the voltage across the capacitor? We start with our capacitor equation. Q is equal to C times V, and they tell us what the capacitance is. It's 2.5 times 10 to the minus 6 farads. The charge is 5.0 times 10 to the minus 5 coulombs. That's the same as 50 microcoulombs. So solve that equation for V. Put in the numbers and put it in your calculator. 20 volts is the answer. Frequently, Capacitors make use of dielectrics between their plates. In many capacitors, the dielectric is a piece of oily paper, but it could be made from any insulating materials. Most materials will polarize in the presence of the charged capacitor, and we can see that in the simulation. Most materials will polarize in the presence of a charged capacitor. The presence of the dielectric affects the distribution of charges on the plate of the capacitor, making the amount of capacitance change when it is present between the plates. In fact, you can see that if I show a gauge here with the amount of capacitance, the capacitance changes as I slide this material in and out in between the plates of the capacitor. The dielectric changes the effectiveness of the capacitor, and that's an adjustment we make numerically using kappa, the dielectric constant. When a dielectric is present, then the capacitance equation changes, and kappa is typically a number that the larger it is, the more effective the material is, permitting the capacitance to increase. Kappa is a unitless number. Kappa is equal to 1 for the vacuum or for air, and it ranges up to a number of about 10 for some glass materials. The higher the number kappa is, the more effective the dielectric is at increasing the capacitance. So there's an electric field between the charges of the plate of a capacitor, and electrical energy is stored there. And we have some formulas for that energy. Symbolizing the electrical energy stored in a capacitor using the letter U, we can write three equations. One of them, U is equal to 1/2 Q times V, where U is measured in joules, Q is measured in coulombs, and V is measured in volts. If you combine that with the capacitance equation, Q is equal to C times V, then you get two other equations. And which equation you use depends on what information you're given about the problem. There's another example in your text. A 4.0 microfarad capacitor is charged to 500 volts. How much energy is stored in the electric field of the capacitor? Let's pull out one of the appropriate energy equations. In this case, we know that the capacitance is equal to 4.0 times 10 to the minus 6 farads, and the voltage is equal to 500 volts. So U is going to be 1/2 times CV squared. Put in the numbers and then solve the problem. I find that half a joule is what is stored in energy in this charged capacitor. Now, of course, the problems are going to become more difficult, and so as a preview of coming attractions, I've selected 3 numerical problems from other texts to illustrate what you're likely to see. Let's give each of them a try. Here's the first one. A circular parallel plate capacitor with a spacing of D equals 3.0 millimeters is charged to produce an electric field of strength 3 times 10 to the 6 volts per meter. What plate radius R is required if the stored charge Q is 1.0 microcoulombs? Now this involves some electric fields, and we have to remember that in between the plates of a parallel plate capacitor, the electric field is uniform, and the formula for the electric field, E is equal to V divided by D. This capacitor is circular, or the plates at least are circular. These plates are separated by a distance D of 3 millimeters. I have an expression for what the capacitance of such a parallel plate capacitor is. The capacitance is equal to epsilon naught A divided by D. Well, if the plates have a radius R, I can say A is equal to pi times R squared. And now I've got a way of putting all this together because I know that there's a relationship between the charge, the voltage, and the capacitance. Q is equal to C times V. So I have a way of getting at the radius of the plates through the capacitance. I have a way of getting at the voltage through the electric field, and Q was given to me in the problem of 1.0 microcoulombs. Let's put all that together. When I take the expression for the electric field and solve it for the voltage, and I put that in for the voltage, and I take the capacitance, the expression for that, and I put it in for the capacitance in the Q equals CV, then I can see that my D's are going to go out. I can solve now for what R is in terms of the other variables. Now let me put in the numbers and see what I get. Now let me serve that up in my calculator and see what numbers results. The radius I get is just under 11 centimeters. Now, I just want to take a look at the units to make sure that meters is what I ought to come up with. Let me do that over here at the left. Under the square root I have coulombs divided by the quantity, coulombs squared per Newton meter squared times volts per meter. Let me remind myself that a joule is equal to a Newton times a meter, and a volt is the same thing as a joule per coulomb. So I could rewrite a volt as a Newton meter per coulomb. Let me do that, and let's look at the units again and say that now I've replaced volts with Newton meter per coulomb. So now let's see what's going to cancel. I have a Newton that cancels, I have a coulomb that cancels, I've got another coulomb that cancels, and I have 2 meters that cancel, and so I'm left with the square root of 1 over the reciprocal of meters squared, which is the square root of meters squared, which is meters. The units check out, and I claim that my radius is just under 11 centimeters.